In this lecture, we talk about natural language processing, specifically using the recurrent neural networks. How do we process and analyze large amount of natural language data? As we know, neural networks operate on vectors. So in order to process language data, the question is how do we represent words as vector? We are going to talk about word representation. How do we use vectors to represent words and train a neural network model? We will talk about one-hot encoding and word-to-vec, including skipgram and CBOW. CBOW stands for continuous bag of words. One-hot encoding is a naive embedding method. Let's take an example to see how this is done. Considering the dictionary V, so here we use letter V, sometimes we use letter Y also to indicate the dictionary with all the words. So our dictionary V contains 3 words: dog, bites, and man. We can use one-hot encoding to represent words. The word dog is represented as a vector of values 100. So we have one other index that we want to indicate the presence of the word there. So there is only one, and the rest are all zeros. Similarly, bytes. Bytes is represented by the vector of values 0, 1, 0, and there is only one. That represents the word bytes, and the rest of the elements in the vector are 0. And eventually, man is represented by 0, 0, 1. We have one other index that we want to use to indicate the presence of the word man. So that's how we represent the whole string dog bites man. If we look at the reverse order, then correspondingly we have the representation of the corresponding words in the reverse order as well. Now let's denote n as number of different words in the dictionary. Each word is corresponding to an integer from 0 to n minus 1. The integer is the index of the word in the dictionary. So let's assume that the index of a word is I. We have the one-hot vector representation of the word, which is a vector of all zeros with a length of n, and the ith element is equal to 1. So then the word can be used by the neural network. The drawback of one-hot encoding is that there is no relationship between words. If we compute the cosine similarity between two words, the cosine value would be 0. However, in the ideal world, relationships between word vectors actually reflects relationships between words, and features of word embeddings reflect features of words. So here we need to find another way. So word-to-vec came out to help with the problem. It represents each word with a fixed length vector and can better indicate the similarity and analogy relationship between different words. There are two important models, skipgram and CBOW. We will look at the models in the next slide. The skip gram model assumes that a word can be used to generate words surrounding it in the text sequence. So let's take an example of a text sequence. So let's say we have a string or sequence. The man loves his son. We use love word, this was as the central target word, and set the context window size to 2. So the context window size to 2 meaning we consider 2 words before and 2 words after the central word. The skip gram model is concerned with the conditional property for generating the context words the, man, his, and son. Given the word loves, the context words are in the distance of no more than 2 words from the central word. Assuming that given the central target word loves, the context words can be generated independently. So we can rewrite the probability as a product of the probabilities for individual context words. Now the conditional probability for generating the context word. So here we use the letter W with the subscript O to indicate the context word, and WC to indicate the central target word. Correspondingly, UO is the representation of WO, and VC is the representation of WC. Here we use the SUMMAX operation on the vector inner product. Assume that we know the length of the text sequence as T. The word at time step T is WT. The context window size as M. And also assume that the context words are independently generated given the central words. Then you can write the rejoin probability for generating all the context words given any central word. So what does it mean? What it does is that it considers every word in the sequence, in the text sequence, as a central word. And here we have the product from t equal to 1 to the length of the sequence. And for each central word, we consider the window with the size of m, which is the number of words in front and the number of words after. And we have the assumption that the context words are independently generated by the given central word, so that's why we have the product here. This product goes for m words before and m words after the central word. Now taking the log, we have the sum instead of the product. And from the SUMMAX function in the previous slide, taking the log of the probability, what we have is this. Taking the derivative with respect to VC, which is the representation of the central word, and eventually what we get is this. And this is what we need for the update rule in the gradient descent algorithm. The continuous bag of words, or CBOW model, is similar to the skip gram model. The difference is that it assumes the central target word is generated based on the context words before and after it in a sequence. Given the context words, the conditional probability for generating the central target word is this probability. And as mentioned, WC is the central target word. We have context words before and after the central word. We have M words before and M word after, because the size of the window is M. So the context words include WO1, WO2, etc. W up to W O2M. Because we have multiple context words, so here we average the word vectors. And let's denote it V0 or VO bar. So then we have VO bar here in the numerator and VO bar there in the denominator. And let's just use the notation WO for all the context words. The likelihood function is the probability of generating any central target word from the context words. We consider each of the words in the text sequence as the central target word. So we have to put the probability together in the product for t equal to 1 up to the length of the sequence. And this is the probability that each word in the sequence as the central target word, and we have M words before and M words after as the context words. Now taking the log, we have this, and notice that this is what we get from the softmax function. What is the derivative of this? We need the derivative of this for the update through in the gradient descent algorithm. So taking the derivative based on the left on the right side, what you get is this, and then eventually this. Notice that how we get the 1 divided by 2m here. This is from VO bar. VO bar is the average vector. So when we take the derivative with respect to just VOI, then only the term 1 divided by 2m is left. This slide compares the two models, skipgram and CBOW. In CBOW, we predict the target word from several input context words, while in skipgram, we predict target context words from single input word.